or more, 10 days since we last met. And I wanted to remind you that in the last couple of classes, what we did is to look at water. And the interesting things about water, mostly with regards to this class, its ability to hold and transfer heat around. And then we looked at heat. We looked at how the equatorial regions have the most concentrated amount of the sun's rays because the rays hit perpendicular, whereas at the polar regions it hits at an oblique angle, and so you spread out the energy. So what happens is, we saw this before break, we have a situation where heat is always increasing at the equatorial regions and cold is always decreasing. But we established that it's not a situation where we have negative infinity, negative 10 trillion degrees at the polar regions and positive 10 trillion degrees at the equatorial region. We established that we've set up convection cells, just like the convection cells in the subsurface, that are the mechanism by which water, with its tremendous ability to hold and transfer heat, moves the excess heat to the poles and moves the excess cold to the equator and transfers this out and makes our planet habitable by life, and also makes for it to be sort of moderate climate. And we looked at this and we said this is what would happen to convection cells from 0 to 90 degrees in the northern and southern hemisphere. These are mirror images of each other, and said this is what would happen if Earth were not spinning. But we know that Earth is spinning, so again, we look at the Coriolis effect. Coriolis effect, for our purposes, right? You were tested on it with this last quiz. However, it's going to also influence how hurricanes track and how hurricanes move. So you don't need to get into any more detail than the fact that Earth is spinning, and it spins out from under airborne objects, but we will revisit it, which is why I'm going to give you just this little brief review of it. So Earth is spinning, and it spins out from under the convection cells that are actually what's happening in the atmosphere. And so we talked about this. We talked about how Earth is spinning, and if a jet takes off at the equator and trying to fly to Chicago, Earth will spin out from under it, and it will end in the Atlantic provinces. This is the same thing that happens to our atmosphere. Another analogy that might be helpful is to think about being on a merry-go-round. So you're on a merry-go-round on the playground, and think about sitting in the center, right where that pole is. You would not be moving around at all. You'd get dizzy, but you're just pivoting about the axis. If you're out by the edge of the merry-go-round holding onto those bars, you're whipping around at a very fast rate. So that's kind of a two-dimensional representation of a three-dimensional situation. The farther out at the edge of the merry-go-round, which is the equivalent of, so think of it as Earth like that, at the equator, the faster you're spinning. And then with regards to spinning out from under airborne objects, pretend you have a squirt gun, right? And you're sitting in the middle of the merry-go-round, you're trying to squirt the person that's at the edge. You will aim the squirt gun, and if the merry-go-round weren't moving, you'll aim the squirt gun at the person at the edge, and you'll easily hit them. But what would happen is if the merry-go-round was spinning fast enough, you squirt the water at your friend who's at the edge of the merry-go-round. By the time the water got there, your friend would be gone. So it would appear that there is a curved pathway to your stream of water from your spray gun, but it's not the case at all. It's that your friend is no longer where you're aiming. So this is similar to the Coriolis effect, that things get spun out from under. And so what happens is you end up with these cells, which is where we picked up, or we left off last time. We end up with these cells. So what happens is you now have 0 degrees to 30 degrees, Hadley cells, 30 degrees to 60 degrees, Ferrel cells, 60 to 90 degrees, polar cells. And it's the same thing in the northern hemisphere as in the southern hemisphere. When I start showing this, people say, oh, do we have to know these numbers? Well, no, you don't necessarily have to know these numbers, but I bet you all know them now. These are very simple, 0 to 30, 30 to 60, 60 to 90. And this is really important from a coarse and then to a medium scale understanding of weather, the way that we'll talk about weather. So what happens at the equatorial region called the doldrums? Air is rising up. It's very humid, and it is hot, and it's rising up. It's called the doldrums because we can't feel wind moving upwards. So if you're in a sailboat at the equator, you're kind of bumming because there's no wind to move you around. Air moves up, and it goes out of the way, remember, of the stuff coming behind it. And then also now we're adding in precipitation. It starts to rain because it gets to the top of the atmosphere, the air mass is cooler, so it's to rain all of its rain out. So by the time it descends at 30 degrees north and south latitude, those of you who were in this class last semester know that's where the deserts are. There's no more moisture in that air mass, so hot, dry air descends. And then it will come back to the equator and come back up. So you have these Hadley cells going like this. And then it's probably convenient or easiest comprehension-wise to start at the poles and say that it's just like the simplified diagram I showed you. All of the air comes up to the top of Earth, like spokes of a bicycle wheel converging at the hub, and it's very, very cold, so it's very dense. The molecules aren't moving very rapidly, so it's dense. So it sinks down through the atmosphere. When it hits the pole, it hits the landmass, it will then spread back out, again, like spokes of a bicycle wheel, and it will go from 90 degrees to 60 degrees, and then we'll come back up again. So we have the Hadley cell, 0 to 30. You have the polar cells, 90 to 60. Those two create an inside-out cell that's moving in the opposite direction of the other two, called a Ferrel cell. And the intersection of the Ferrel cells, the Ferrel cell with the polar and Hadley, are what make violent weather. Not always, but a lot of times. The huge tornadoes that we'll talk about, F5, if you saw the movie Twister, Finger of God, those happen as a result of what goes on at the convergence between the Ferrel and the Hadley, or the Ferrel and the polar cell. So you have this inside-out cell that's moving from 60 to 90 that meets up with the other two cells. So it's kind of like a figure eight with an added layer, because air can go from the Ferrel to the Hadley to the polar, sort of goes back and forth, and it's in this way that the heat, again, is transferred to the cold is transferred to the heat. We have a warm, temperate climate overall. The reason, recall, that this happens, that the two cells I showed you in the simplified version get split up, is because of the Coriolis, because Earth is spinning out from under them. So you also have to add in this layer that, so maybe it's best to look at this in cross-section. I'm going to skip over this for now and then show you this. We'll go back. So now we're looking at them in cross-section. There's the equator, the dashed line. Here's the pole right here. We're looking in cross-section. And what's happening is these cells are just trying to do this, convection cell. The complicating factor, again, is Earth is spinning out from under the cells. And also, we use as our frame of reference, not that Earth is spinning, because we are on Earth. We use as our frame of reference, the air is whipping past us at 1,037 miles per hour. So what happens is those cells are actually moving all around the Earth and creating these winds. Again, Earth is just spinning out from under them. And this is a good thing if you're confused at all. It's a good thing to look at YouTube or other videos. There's a lot of good videos that show animations of this. I don't want to take time to put a bunch of video clips up, but really nice YouTube videos that will show you convection cells in the atmosphere. There's the first three that come up. If you type in atmospheric circulation, good things to watch if you need more clarification. So the cell's moving around like this, and it creates trade winds. And it creates, as we'll see, back up to this picture. Oops. Creates the trade wind. So there's the Hadley cell. You have trade winds. These winds are the winds that you learned about in elementary school and middle school about the trade. So trade winds go from the east and travel west. The westerlies are a result of the Ferrel cell getting smeared around Earth, or Earth spinning out from under them. And westerlies come from the west and travel east because that cell is moving in a different direction. And then the polar easterlies are a result of the polar cell, just again trying to go like this, but are spinning out from under it. So we say that it's going around like this, like a ribbon around all of Earth. So winds are created in different directions. The same thing in the northern hemisphere as the southern hemisphere. And it's, there's a lot of stuff in this picture, but really it's pretty simple, right? You have three cells in the north, same thing in the south, 0 to 30, 30 to 60, 60 to 90. They're doing this convection because of temperature and pressure differences, and Earth is spinning out from under them. So the names of these are all on here. But these are important because they're going to show, or they're going to dictate where large hurricanes are, what path they take, where you can expect to find, again, huge tornadoes, and what will happen up in the atmosphere. So that's the basics of this. Wind is air moving from one place to another. Now, to complicate things, we have to talk about why air masses rise, why air masses shrink, why they go up, why they go down. And so this principle is going to be really important in thunderstorms. This is called adiabatic heating or adiabatic cooling. And the definition of adiabatic heating is a temperature increase without any heat addition. Adiabatic cooling is a temperature decrease without any removal of heat or energy. Now, how can that happen? Well, there are three factors here. One, the volume of the air mass. Two, the temperature of the air mass. And three, how much energy, how many calories are in that air mass. So we have to take these three things together. And what's going to go on is, maybe I'll show you the next picture. I'll show you this for now, and we'll go back up to this. This might be a better way to show adiabatic cooling. So what happens here is you have an air mass. And the air mass is filled in the troposphere down here with gases. The gas we are interested in is water vapor. And we know from our discussion of many different things that air, or that vapors will take up as much space as you'll give them, right? If I had a little burner down here and put a little pot of water here, the vapor would take up this whole room. So vapor will take up as much space as you give it. Liquid takes up less space because the molecules have to be touching. They slide past each other. So in this case, we have air here in this imaginary constrained cube at the bottom of the atmosphere, where the atmosphere is pushing down on top of it. So just like when we talked about how sedimentary rocks form, right, by the weight of the overlying material, the atmosphere has weight to it. There's gases, a thick blanket of gases, and pushing down because of gravity, or gravity pulling it rather, on the stuff at the bottom. So this air mass is constrained, and it's being pushed upon, and so it has a certain volume that gives it a temperature and gives it amount of water that's in it. As it goes up, what's going on is it's under progressively less pressure. We looked at this when we talked about volatiles in volcanoes, right? So under progressively less pressure, when you put gas under less and less pressure, it will expand, take up as much space as you'll give it. Expanding it causes the amount of energy, the calories that are in that air mass, to be spread out over a larger area. So without any addition or removal of calories, of energy, of heat, the temperature will drop. And so in this picture, you see as the air mass rises up, it expands to its maximum amount at the top of the atmosphere. You spread those calories over a larger area, so the temperature drops, and now you have the vapor that was in here turning into liquid in the form of small droplets, or even ice in the form of crystals. That's going to make for rain, or in extreme cases, thunderstorms, which will make for tornadoes and hurricanes. So very, very violent phenomena come about as a result of this simple process. The example that I've given before is that, so I decide I'm going to blow up a balloon. Your lungs have about 2 liters of air in them. My body, as you know, is about 98.6 degrees. So I blow up a balloon. Now you have my 2 liters of air from my lungs in this balloon sitting here at sea level, and it's 98.6 degrees, and maybe I've blown 100 calories into it, whatever, some number of calories into it. And now you cause this balloon to float up through the atmosphere. The balloon will naturally expand. At some point, if you let a balloon go, a helium balloon, any sort of balloon, and you let it go up through the atmosphere, it's going to burst. It's going to burst because the air will put so much pressure on the material that it will just pop. So you have the balloon rising up through the atmosphere. Now it's up to 5 liters because there's less pressure on it. Those 98.6 degrees are still in it. That's still the temperature. But you've spread those 100 calories over double the area. So the temperature, the 100 calories are in it, so the temperature will go from 98.6 degrees down to 40 degrees. So you're spreading the energy out over a larger area. You're not removing or adding heat, but spreading heat over a larger area will cause the temperature to expand and contract. Another way of thinking about it is maybe it's cold in this building or heat's broken in here. So if somebody has a little space heater in their little office and it's nice and warm in that room because you have a space heater in a small area, and then we say, hey, we're cold too, and so you bring that space heater into here and put it on, and it doesn't get nice and warm in here because we have a huge area. So you're spreading temperature over a larger area, and that will cause the temperature to rise or fall. The opposite can happen too. When those cells are descending, air at the top of the atmosphere, now the polar cells, air at the top of the atmosphere is very dense, and it's sunk, and it comes along the land surface, so that sinking naturally causes it to rise, and this is the driving force of weather. The temperature at the top of the polar cell may be 0 degrees, but it's moving in this convection cell. You take 0 degrees. There is some energy in there, and you constrain it into a smaller and smaller and smaller area as it goes through the atmosphere and gets under more and more pressure. By the time that air mass gets to the land surface, it could be 40 degrees. Then you've not taken out or put in any energy. You've just concentrated the energy into a smaller area. So that's adiabatic heating. And the other way is adiabatic cooling. Rising and expanding causes temperature to drop. And condensing and dropping causes the temperature to rise. Make sense? So that's a picture of adiabatic heating and cooling. And if you put them together with this, and I'll show you this again in a minute, put them together with this, with these cells, and the fact that air masses are always rising and always dropping, you end up with a situation like this, where you have warm air, molecules are vibrating very rapidly, you have a high temperature in there, that causes it to be less dense, which causes it to rise up, but the process of rising it up causes it to expand, which causes the temperature to drop, which causes the molecules to vibrate less rapidly, which causes it to be more dense, which causes it to fall down beneath the stuff above it, which the process of contracting causes it to warm. So you have to sit with this a little bit, but these are simple principles. And again, I can put some links on Canvas, or this is a good thing to look on YouTube and look at some videos of this because the animations sometimes help. But these simple principles will make for, again, a solid understanding of thunderstorms, hurricanes, and tornadoes. So, adiabatic heating and cooling. And there is the, again, picture of the cells turned sideways. Now we're going to start looking at the jet streams. The jet streams are very turbulent intersections between these cells. We have interesting weather in the mid-latitudes, and the reason we do is because we have competing polar and tropical air masses. And that is where energy is transferred. The process of transferring energy makes for severe weather. So these cells are up, the jet streams, high up in the atmosphere. We're going to look at the jet stream in a little more detail. The interesting thing about these is that, maybe this is a good time to say it, if you look at this, think of Earth not spinning again, and think of those cells just staying where they are, right? So if an air mass passes over Chestnut Hills, it goes up in the atmosphere, and it will pass back over Chestnut Hills in a way that, since Earth is spinning, will pass over Chestnut Hills, and then when it comes back down, that same parcel of air will be over the Pacific Ocean, because Earth spun out from under it, right? So if this is not spinning, what happens with the jet stream is it's just an air waterfall. It's a wind waterfall. These two things are rushing downhill, straight downhill. That's all they're doing. So think of, wind waterfall, flying down from the top of the atmosphere to the bottom. But you all know the jet stream, I'm sure, and I'll show you in a little more detail. Because Earth spins out from under it, our frame of reference is that we have this wind that's rushing past the United States. Again, it's not rushing past us at all. It's trying to go straight down from the top of the atmosphere to the bottom of the atmosphere as those cells converge and come down. But because of the spinning, we'll see how we deal with this. So maybe some of you went to California over spring break. I pulled this off of the American Airlines website. And this shows travel times, etc. And the travel time here is not adjusted for time zone differences. So this is absolute travel time. What do you notice about the travel times going from Boston to San Francisco versus coming home at the end of spring break? Same time, the same distance, right? Same time? Which one's more?
It takes an extra hour to go from Boston to San Francisco.
Excellent, why? Why does it take an extra hour? That's what I'm here for, right? Because what?
This is because coming back, like, the jet streams are with you, so it's faster.
Exactly, exactly. The airlines love flights that come from San Francisco or anywhere in California and come to Boston. They don't have to use a lot of fuel. They fly very quickly. They get you here an hour earlier. Why? Well, because of this. I'll just put these all out so you can look at them. Because of the jet stream. The jet stream is 8 miles up, so we don't get blown away when we are standing in the position of the jet stream. But it's a belt of winds that goes from the west to the east. Again, we're talking about just our country right now. And it's because of these competing tropical and polar air masses. So now we're talking about the intersection between the polar and the Hadley cell. Sorry, polar and Ferrel cell. But the Ferrel cell still has a lot of temperature. And the hot, cold stuff that we'll look at is really relative to each other. So certainly the Ferrel cell is colder than the Hadley cell, but it's still very, very warm relative to the polar cell. Again, because of the way that Earth tilts, you're warming the Ferrel region more than you would the polar region. So you have this polar air that's cold that lies near the surface. You have tropical air that's warm and it's at the top of the atmosphere. And the interaction, again, it's about 8 miles up, makes a wind waterfall that goes straight down from the top to the bottom of the atmosphere. But because we're spinning out from under it, it's a belt of winds that's 1,000 kilometers wide. It blows anywhere from, as you can see, 120 to 300 miles per hour. And it changes seasonally. And this is important. The whole adage, if you don't like the weather in New England, wait a minute, it's because of the jet stream. So recall that the Earth tilts, right? So if the sun's over there, when we are tilted towards the sun in the northern hemisphere, those convection cells are going to smear upwards. And when we are tilted away from the sun in the northern hemisphere, they're going to come downward. So the polar cell will come down a lot farther. The Ferrel cell will go down farther because you need, and the Hadley cell will go south of the equator, right? Because the equator is moved upwards. So now maybe where my elbow is, which is in South America, that's where the equatorial region would be and with the tilting. So what happens is this belt of winds will change. Here is a diagrammatic representation of the seasonal aspect of the jet stream. And once again, we have to talk about our frame of reference. It's not that the jet stream is moving up and down. It's that Earth, in addition to spinning, Earth is moving in this direction. So the jet stream, the interaction between the polar and the Ferrel cell will move up and down. But again, it's staying right where it is. Earth is coming out from under it. So what you see here is that in the winter, you have this compressed polar air in the whole region above that blue line. This is the demarcating line, the dividing line between the polar and the Ferrel cell. So Earth is tilted away from you if the sun's behind you. And so the polar cell dips down over much of this area. You look and see that the New England area is really kind of in this, and you'll see it more in the next picture, in this path of the demarcating line. So when it's winter, when Earth is tilted away from you, you have a situation where you're in the polar south. And that's why, not this winter, but in other winters, it's been very, very cold. You're sitting in the polar south. Then as Earth starts to tilt back towards you, you have the spring, and for reasons that we'll discuss later, it actually moves up high over over the Pacific, essentially it's because of the influence of the Pacific Ocean, dips down a little farther, so you have colder weather in this little portion, according to this idealized diagram, in the spring than you do in the winter, and then in the spring it's right up over us in Boston. This is a reason why you can have an 80-degree day in the spring, and then the next day you can have a 20-degree day, because the position of the jet stream dips slightly lower or slightly higher. So then in the fall, right, Earth is now starting to tilt back again, and it's moving up. So we did winter, spring, summer, so we go up to the highest one, right? If you've ever traveled and you're in a hotel and they shove USA Today under your door and you see the full color map of the temperatures on the United States, you see they're all red, right? Red and orange. Because the polar cell is way up over northern Canada, and we are squarely in the Ferrel cell, or even sometimes can be in the United States in the Hadley cell, hot temperatures. So that's when Earth is tilted towards you, again, if the sun is behind you. And then in the fall, it starts to grind backwards, and so it dips down a little more. So again, this is the dividing line between the polar and the Ferrel cell. And the intersection is where there's going to be potentially very violent weather, including huge tornadoes. So that's an idealized diagram. Here's an actual diagram of the jet stream. This was a couple of months ago, so it wasn't, a couple of months ago, so it wasn't last week. But what you can see here is what? Will you tell me? On Wednesday, what was the temperature like in Boston? Very, very cold, right? It's firmly entrenched in the polar stream. And when we'll talk about rivers next, and you'll see that rivers wind back and forth, and sometimes they wind back and forth so in such a current fashion that they can actually cut off a bend of the river. The jet stream can do the same thing. So what you'd expect if you have this big bend is sometimes it will just punch through a new path and isolate that bend that dips way down, and that will just sort of go away. The wind rushing downhill will stop. So it was really, really cold in Boston on Wednesday. How about Thursday? May have gotten a little warmer, but we're still firmly in the polar cell, right? Because that line is the dividing line between the polar and the Ferrel cell. What about Friday? This is where you can have turbulent weather. So there could have been a storm, maybe not, but maybe there could have been a storm, or you could just have unsettled weather, the intersection of these two. And then Saturday, what would you think? Suddenly pretty warm. So from a regional sense, again, anything south of the yellow line is warm, anything north is cold, and if you're right on that line, then you have unsettled weather. So that's the jet stream, and we will return to the jet stream as we apply it to violent weather, but for now, just understand what it is. This belt of winds, 8 miles up, 1,000 miles high, and it travels at very, very fast speeds. And so the answer to this question of why does it take an hour less to fly home is because pilots can get into the jet stream when they're coming from San Francisco to Boston and just essentially float like you'd float on a river. You use a lot less fuel and you travel really quickly. When you're going from Boston to San Francisco, you either have to change your flight pattern to get out of the jet stream so you don't have a potentially 300-mile-an-hour headwind, which is pretty troubling, so you have a longer path, or if you're in it, then you're burning a lot of fuel and you're having to fight 100 to 300 mile an hour headwind. And yeah, it's really neat to think about the fact that it's not a headwind at all, it's simply air rushing downhill, but we're whipping out from under this thing. So pilots have a lot of work to do. So again, these are fundamentals that we're going to put all together when we talk about weather. So the last 3 parts of this, or last 2 parts of this, are regional air masses, and then we'll talk about fronts. So this is a picture of regional air masses. Again, we're doing the United States because this is where we are, this is where we live. The rules for this picture are very simple, and you'll get it in 2 seconds. You'll understand it. It's intuitive. If an air mass comes from over water, it's wet, and land, it's dry. If an air mass comes from the south, it's hot, and the north, it's cold. That's it. So knowing those 2 things, you can intuit all of the air masses that are coming into our country or our continent, and this is what is going to make for very violent weather when these air masses that have different temperatures and water content, right, going back to the first couple of slides in this, when these air masses meet, when there's a gradient, recall from the first day of classes, nature will seek to equalize out that gradient, and it does so when there's a severe gradient in a violent way. We said also the first day of classes, the number one thing we expect from climate change is going to be more storms. There's going to be more storms and more droughts and more of these weather-related changes as a result of climate change, because we don't call it global warming anymore, because there are actually places that are going to get colder as a result of global warming, so we call it climate change. So places are getting colder, places are getting warmer, places are getting wetter, places are getting drier. That's making for more severe gradients in our country and elsewhere. This is why we're having more tornadoes, more thunderstorms, more hurricanes. So with regards to this picture, again, it should be very simple to you. Start here, I guess. Air masses coming over Mexico are from the Hadley South. So the air mass came up from the equator, rain, 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 rain. Also, when air masses are over the continents, there's no source of moisture being added, so it gets dry. You have an air mass that's riding up over Mexico. It's very, very dry, but it's very hot. And so this is one main air mass in our country, right? You think about the Southwest. They say it's a dry heat. That's where people go to retire because it's nice and warm, but it's dry. And old people complain of aching in their bones when it's humid out, right? So it's dry, hot areas. We'll talk about desertification, about droughts and deserts. In this case, this is not a desert because of things humans did wrong. It's because that's naturally the climate of that region. Hot air coming up over Mexico. These two air masses are about the same situation. You have hot air, and since they're coming up from the ocean, it's wet air. So you have hot, wet air coming up from here or from here. And here's where we watch, right, for hurricanes, the big hurricanes, hurricane season right now. Because you have very, very hot air that has a lot of humidity in it. And when you start pulling the temperature out of high water content air masses, you're going to make very, very bad things happen. So then coming from the north, continental Arctic. This is air that comes from over the northern parts of Canada, and it is dry because it's coming from land, but it's also very, very cold because it's part of the polar south. And also in general, not in general, also absolutely, the warmer an air mass is, the more moisture it can hold. So an air mass coming from the north is never going to hold anywhere near the amount of water that an air mass from the south is going to hold. So you have very, very cold, dry air there that will transition into cold-ish, dry air. So this continental Arctic will come into continental polar. So cold, dry air coming from the north, very hot, very wet air coming from the south, and then the where we are, so the middle part of this, you have air coming from off of the water, so it's wet, but it's not as wet as it would be if it were coming from the south because it's cold. And again, cold air can't hold the moisture that hot air can hold. So these are, again, intuitive relationships. You should have an intuitive feel for, obviously air comes from hot, wet areas. It's going to be hot and wet. But it's the intersection of these that will start to make for violent weather from a regional sense. So we went from a global with regards to convection cells to a regional sense, again in this country because that's where we happen to be able to do this for any other country, and the results will be the same. And then we'll go down to a local sense, and this is where we're starting with thunderstorms essentially. We're talking about fronts. And there are three types of fronts, and with the end of these three types of fronts, we will start looking at tornadoes, hurricanes, thunderstorms. One of them, they're all the same actually. We'll see they're all the same, but things set them spinning. So I mixed them up because they're so similar. So here we have a cold front. And when air masses meet, again, you take these principles that we learned before break and today, and apply them in the same way. An air mass that is hot, it tends to have more moisture in it, though not always, right? See the southwest. And the molecules are vibrating very rapidly, so that air mass is much less dense than cold air. The molecules are not vibrating as rapidly, so it's more dense. So what's happening in this picture is the fronts are named after the air mass that's doing the moving, that's moving. So this is a cold front. Cold air comes into an area, and what it does is to lift the warm air up very quickly and very high. And so those teeth are, if you see those blue teeth on a weather map, on a two-dimensional weather map, you know that that's a cold front, and you know that's the direction in which the cold front is moving. So this air mass comes in. So say you're standing in Boston in the summer, you're taking a summer course. Standing in Boston, and it's oppressively hot and humid, you're really uncomfortable. And then you start to hear, right, rumbles of thunder. We'll talk about why there's rumbles of thunder. And then you have the thunderstorm, which again, I'm sort of skipping over that part for now because we're going to talk about it in more detail. And then after the thunderstorm, it is a situation where you feel cooler, right? It's cooler, and the temperature is much more reasonable than it was before the thunderstorm, at least for some period of time, because a cold front came in, and now you're in the cold air. Once again, cold only relative to the hot. It's not like you're suddenly in 30-degree air, but you're in colder air than the hot, sticky air you were in before. So the cold air is coming in. It causes the warm air will always go up on top of the cold air, to rise very high very quickly. And so you know what happens when you take an air mass with a lot of moisture in it, and you start rising it up because of adiabatic cooling, it's going to expand. The expansion causes the temperature to drop. Now we add the water part to this. When you drop water's temperature, you go from a vapor to a liquid. I'm not speaking slowly because I'm being condescending. I'm making sure I say this right. You go from a vapor to a liquid, but the process of doing that, right, because of the high latent heat of fusion, will release calories into that air mass. So that warms the air mass, which causes it to rise and expand even more. But the expansion, adiabatic cooling, causes the temperature to drop, which causes more water to turn from a vapor to a liquid. And in extreme cases, it will turn to a solid. And every time you change phase, you add heat to the cloud. So it's this self-perpetuating cycle that adding heat to the cloud causes it to rise and expand. But the process of causing it to rise and expand causes the phase to change from vapor to liquid and potentially again to solid, which causes more heat to go. And this keeps on going until you exhaust all of the water vapor out of the cloud. Till all of the water vapor turns into a liquid, so rain falls, or solid, so hail falls. And it's only when you have no more vaporous water to change phase into a liquid or solid that releases more heat into the cloud to drive this heat engine higher, that you then end the situation. So I'll repeat that when we talk about thunderstorms. But what's going on here? Again, the air mass is rising and expanding, rain will start falling, and in extreme cases you'll have a thunderstorm rather than just a rainstorm. And then you end up with cold air in that region, the thunderstorm's over. This is an incredibly violent type of front, potentially, and it is pretty quick. You know that you don't have, if you're sitting in a thunderstorm, you don't have a thunderstorm for more than maybe a minute or two, right? If there's more, then it's multiple clouds coming in doing the same thing. Very, very brief, violent, intense changing around of heat. So that is a cold front. How does a cold front differ from a warm front? In the warm front, the warm air is doing the moving. So there's the meteorologic symbols, semicircles, half circles, and they're pointing in the direction in which this front is moving. So in this case, you're in a cold situation. The air mass is cold, and warm air is coming into the region. And again, what happens is warm air will always move on top of cold air because it's less dense. So think of oil and water, right? Water is never going to ride on top of oil. And it's the same thing with warm and cold air. Warm air is less dense, it will always go on top. There's no situation under which almost no situation in which cold air will go on top of warm air. So in this case, warm air is coming into the region, and it will go up on top of the cold air that was in that region. But in this case, it will go up very gently and slowly, and it will give a lot of time for the transition. And so you can have some rain or a lot of clouds, but you won't have violent things like thunderstorms, tornadoes, hurricanes, because it rises up slowly. It gives a lot more time for the water to change phase and the energy to dissipate. So you won't have a thunderstorm in a warm front, but you have rain, depending on how you lift up that air as it's also pushing. So if you saw an animation, it's going to encourage you to look at some animations, cold front, warm front, included front. That whole air mass is moving, but you have this front of rain that goes for potentially a wide area, depending on the size of the front. And then the last kind of front is really a mix of the two. And what happens is, so I'll show you first, or we'll look first at one part of this diagram, then we'll look at the other. So look first at sort of this part here. And what you have, this is called an occluded front. You occlude something, you isolate it, right? So in this case, you have a warm front. So it's like the previous slide. Warm air is coming into the region and starting to rise up. But then behind it, you have a fast-moving cold front that overtakes the warm front and lifts all of that warm air up into the atmosphere in this kind of diamond shape or inverted triangle shape. So you had a warm front coming in, so just that wedge, cold front coming in and lifting it up in the very violent way that it can be lifted up. And so in this case, what you have is rain that will last for days. Then the area, it may move a little bit in some directions, but you have essentially warm air that has a lot of moisture in it lifted up high into the upper part of the atmosphere, and it will cause the water to change from a vapor to a liquid for a very long period of time. So this is where you have rain for a huge region, for several days. We've all been in this situation, especially in Boston. Sometimes we have these occluded fronts, and it rains for 3 days. So an occluded front is simply a warm front that gets overtaken by a cold front, and you end up with widespread rain for a long time. But it is the first one, the cold front, that is the most important to this class, swapping slides here, because the cold front is the one that will create thunderstorms, and as we'll see, thunderstorms will create tornadoes and hurricanes. So as long as you have an understanding of a thunderstorm, a good solid understanding of a thunderstorm, it is no stretch to understand hurricanes and tornadoes. And looking ahead, after we finish with weather, we're going to move into flooding. We're going to do a lab exercise about flooding. So flooding is what happens when all of this rain actually hits the ground. So these are related. So to recall, there are places, I won't go over this again, there are places in the United States where you expect violent weather because the air masses that come together are incredibly different in temperature or moisture. So thunderstorms, we said this already, but I'll put it out again. And I'm going to show you a diagram. I'll show you a diagram and we can talk about this as well. So remember, we're talking about cold fronts here. And what happens is, so now you don't have to think about moving, just think about the air mass sitting right here. Hot, hot air, it's wet, and it is very, very hot. The molecules are vibrating very rapidly. The air mass rises. The rising causes it to expand. The expanding causes the temperature to drop. The temperature drop causes water to change from a vapor to a liquid. The changing of phase causes heat to be released into the cloud, which keeps it rising. But that rising, again, causes the temperature to drop, which causes the water to go from a liquid and then eventually to a solid sometimes, especially in the case of these cold fronts. And so you have rain falling in one side, and it's actually, as you'll see in the next picture, a well-developed area, these thunderclouds, where rain is falling on only half of the cloud, because there's a downdraft side where the rain is falling. Water has changed from a vapor to a liquid to a solid, to a supercooled solid, which will shatter, as we'll see, and become unstable at the atomic level. you have this downdraft side where it's raining and hailing and raining and hailing. Sometimes hail, which is ice crystals, right? Hail will form in the clouds, but by the time they hit Earth, they've changed back into water. Sometimes they don't. So you have the downdraft side where the changing in phase causes rain to fall. The updraft side is where, as long as there is vaporous water in the cloud, it's going to rise and expand. And every time there's a change in phase, it adds heat to that side. So one side has this updraft, updraft, updraft until there's no more vaporous water. The other side has the downdraft side because that's where the rain and hail will fall. So this is what happens. You have this warm, humid air that rises and expands, condenses into clouds, and every time it releases heat, it rises even higher. PPT stands for precipitation. Ice crystals will form, and they get heavy, and they fall down, and that is, again, rain and hail. So here's a picture. Downdrafts will actually drag in so much cool air that they squelch these warm, moist updrafts eventually. So these are the 3 stages of a thunderstorm. Here's the initial stage called the cumulus stage. This is where you just see the sky start to be gray, but there's no rain yet. The air mass is rising and expanding, rising and expanding. The mature stage is what I just described in the previous slide, where you have updrafts and downdrafts. The downdraft side is where the rain and hail come down. The updrafts is where the heat engine is driving it higher, higher, and higher. And then when you get to the point where there's no more vaporous water in the cloud and these reactions, these changes in phase have been exhausted, we're going to layer thunder and lightning on top of this, then you have a last stage called the dissipating stage. There's this icy cap on top of the cloud. There's no more thunder and lightning, and it's just downdraft, and you end up with this tapering off of rain. The last bit of energy is expended from this particular cloud, and then you go back to, all the moisture falls, you go back to a nice sunny day. So that is the water part of a thunderstorm, but now we have to add in lightning. By the way, now that you're back from spring break, those of you who have been in a plane, I should tell you that the downdraft side of thunderstorms are pretty dangerous. Flights, Pan Am 759, that was back in the 80s, was leaving New Orleans, and it got caught in a downdraft, and it killed 145 people on board and then 8 people on the ground. To take off in one of these can slam the plane to the ground. Also in the 80s, Delta, flight leaving Dallas, killed 133 of the 163 passengers. Nothing wrong with the plane, but it took off, and the downdraft just slammed it to the ground. It is not dangerous from a lightning point of view, because when lightning hits a plane, it just gets directed around the plane. Nothing happens. So you have to worry about the drafts rather than the lightning. So what is lightning? We'll look at thunder and lightning both in this slide and the next slide, and then we'll be done. So this is also important. This is going to add a lot of energy to the cloud. So what happens in the process of this heat engine is sometimes it's rising so high and the phase change is going on so rapidly and energy is being removed that water molecules will become unstable and they'll shatter. They shatter at the molecular level. And when they shatter, what happens is charged particles will build up in different parts of the cloud. So you have pockets of positively charged particles, pockets of negatively charged particles, and then when you have these charged particles build up, air, remember, is an insulator. We talked about how air is an insulator, so just like temperature doesn't want to go through air, also electricity doesn't want to go through air. But at some point, there's so much of this energy that's built up, different charges, that they will equalize out. They will equalize out in a violent, pretty instantaneous way. It's 55,000 degrees we're talking about. The atmosphere going from 30 degrees to 55,000 degrees, which is multiple times hotter than the surface of the sun, and it's traveling at 10,000 miles per hour. So there's a very, very violent situation. Here's a picture of the charges moving to the top of the cloud, other charges moving to the bottom of the cloud. They build up. In response to that, you have these induced positive and negative charges that are building up at the bottom of beneath the cloud, and these will equalize out. I'll finish up talking about this, and we'll maybe recap it a little bit next time since we're out of time. But for now, that's the nuts and bolts of thunder.